Hello everyone. In this chapter, we are going to learn about the response surface methods. So far, we have learned that, for example, when we have linear relation between our parameters, how can we calculate the betas, right? But in this chapter, we are going to see that, okay, what happens when we call the situation that, for example, we need to use one of the response surface methods like central composite designs that we would use. So I'm going to share my notes. We're in chapter 8. And you can, if you go to the Montgomery book, it's going to be on chapter 11. It talks a little on chapter 6, but it's going to be like a few pages. And then, but the main parts of the response surface methods in the Montgomery book is, and you can see that in chapter 11. Also, the course material, as I said before, is like the copyrighted from Professor Alex Benlidis. The only thing is that in this chapter, I've added some background information, like more explanation. And you can see that for the page that I've added, it's just I put the source, like the reference, which is our reference book, on the bottom of the page. But generally, it's coming from the Professor Benlidis. So our objectives are the uses of response surface methodology. We want to learn about that. We want to understand the methods for locating an appropriate experimental region. We want a description of designs for fitting response surfaces, and we want to see how to use the polynomial model to fit data from response surface designs. And in fact, we want to establish an optimal window or map. We use the response surface methodology mainly for optimization. So here is that as an introduction. Many times the goal of experimentation is to characterize or model the relation between one or more responses and several factors or inputs. So often the exact mathematical relation between the response and factor is unknown. So in fact, we are trying to find out the empirical model, which is going to be our best approximate model with the response surface methods. A very useful class of approximating functions are polynomial models, often of degree 2. And for polynomial, we would use the Taylor series, right? It's written here. We would use the Taylor series expansion for the true underlying theoretical function truncate after terms of the DF order. And the polynomial model can be thought as the French curve or fitting a spline. So we have all of these ones in I'm not sure if you remember it or not, as this is a grad course, but in our first year engineering courses, we have one of them is engineering computation. So all of these Taylor series, like fitting a spline, all of these have been covered in the engineering computation course. At UW, we call it CSG 121. But even if you don't remember it now exactly what was there, we are going to cover them, so don't worry about it. I've added something for it. Okay, let's see what's the response surface models. What do we call a response surface model? Look at here. This model that you see here, it's the first order. It's like beta 0 plus beta 1 x1 plus beta 2 x2. Even let's say we have beta 1 2 x1 times x2, like the interaction of it. It's the first order, right? And when it's the first order, it's like if you draw it, it's going to be a fluid plane. In the second order models, when we are looking at it, we have the intercept like beta 0. We would have the main effects. We are going to have their interactions, and then we would have something that we call it curvature. So for the curvature, it's like that we would have beta 1 1 x1 power 2 plus beta 2 2 x2 power 2. Whenever we have this second order, we call it second order response surface model. the result that you get. All these y that you see, these are our responses, right? The responses of our model. And when we have the second order, when the y comes from the second order model, so we would call it the second order response surface model. It's like the surface that we would have for our second model. And we have the curvature, right? So it's like here you can see it's a power two. With linear design, 2 levels, we cannot in general make good prediction inside experimental region. Using more than 2 levels in the design will allow more complex modeling of the response variable. We can estimate all of these parameters of beta 0, beta 1 from the equations that we had in chapter 2. Maybe this slide number would be a little different, like maybe it's a slide 6 or 7, because I always add more to the original notes that we got from Professor Penlagis, depending on the, like, if I see that there are questions on some specific part of the background, so I add more to that. Or maybe a little, like, as I said, it's not exactly slide number 5, just go, but we have it in chapter 2, all of those beta, we would say that x prime x power like -1, if you remember it, so based on like those ones. Okay. We talked about center points a little. So now let's go to the like main reason that we are adding these center points. So far we said that we are adding center points to find out the pure error in our for our runs, from our runs. So based on the idea of replicating some of the runs in the factorial design. So if we have full factorial, so we would full factorial replication, we are gonna replicate the whole design that we have. But if we have the partial factorial replication, for the partial ones, we would use the center points, which I'm going to talk in a few minutes about that. And then we're going to run them. Runs at the center, and it's almost center of the, like, for example, if I have temperature in the lower temperature of 30 and the higher temperature of 50, so the center points, the temperature for that center point is going to be 40, like it's going to be exactly almost between 30 and 50 if I have. So runs at the center provides an estimate of error, which we call that pure error so far, and allow the experimenter to distinguish between 2 possible models. Let's see what does it mean. We said that we have the first order model, like we have interaction, and we have second order model. For the first order, we didn't have these like x power 2. Now, when we say that it's like that estimate of error, when we want to find out, it helps us to find out the pure error. But let's see, how can we make sure, we want to see, how can we make sure that, for example, our second order model is a better fit for our, comparing to our first order model for this set of data that we have. And the only difference between them is this curvature term, right? It's like this, or curvature, is like this x power 2. So there should be some connection between them. When we have the, look at here, look, so here, what do we have is that we have the just first order, like I have 4 points, right? And then I'm gonna add a center point. So let's say we have 5 independent runs totally. I'm talking about the first model. If we said that we are comparing like these 2 models, right? So for the first model, let's say I'm gonna have something like this. I would have there, like I would consider the interaction and then the main effects. Let's say these 4 runs, and then I will add an extra run as these, and would call it center line. And here we have 2 factors. It's 2 power 2 design with a center point. So when we look at this like this, and the reason that we add this center point is that if you look at the equation of the beta 0 plus beta 1 x1, right? It's like this. We said we have x1 and x2. So it's going to be beta 0 plus beta 1 x1. So I'm counting the parameter. Beta 0, beta 1 x1, beta 2 x2, and then beta, let's say 1 to x1 and x2. So it's like that when we are counting all of these parameters, we will see that, for example, if I add a center point, I can find a better estimate for my model. Let's look at here again. So let's say we have 5 independent runs totally. So this center point, when we are adding the center points, the number of the center points, we are going to have replication in that center points. And then we can get the average of it. For the average of it, we call it y bar of the C, like y bar at the center points. And then we would have the y, we can get the average of at this point, for this run, this run, this run, and this run. Before I go to the next slide, and then you can see the answer of my question, think about it. If my center point, the average of my center point, it's almost the same as the average of these 4 lines, 4 points of the corner points. What's gonna give us? Think about curvature. So if the average of the replication at the center point, which I'm going to show you, call it y bar C, if it's equal to the average of all of those runs on the like factorial, we call them factorial runs, the average is the same. What does it tell us? You can pause the video here, think about it, think about the question, and then come back and listen to the rest of it. So if the average of them, they're the same, in fact, it means that there's no curvature, right? So I have let's say I have something like this, and the average of these 4 is exactly the same as the average of the replication that I have at the center points. So it means that there is no curvature, it's just a plane like this. But if I have a curvature, let's say like this, it's going to be like, I'm trying to make it in a way that it would make sense. Like if it was like this, in that case, you would say that, okay, so the average that I would have on the center point, and it's more or less than the average of the corners that I would have. So we would say if curvature is not significant, it's almost 0, we would say the average of the F, these are the factorial runs that we have on the corners, is going to be equal to the average of the center points, like the replication that we would have on the center point. And most of the time we have the, like in the industrial application, we have like between 3 to 5 replication in each of these center points that we are talking about. So there is no curvature. And when there is no curvature, we would have beta null, beta 1 x1, beta 2 x2, beta 1 2 x1 x2, plus like error that we would have. And then we can have the hypothesis for it. So the hypothesis would say that the beta II is equal to 0. And then the alternative hypothesis, it would says that the beta II is not equal to 0. And when we say beta II, it means that beta 1 1. So beta 1 1, it's the way that we named it here, like it's from the Montgomery book, you can see the source of it. It's like there's beta 1 1 x1 power 2, right? Over, like, look at here, it was beta 1 2 x1 x2. So if I have beta 1 1, it's going to be beta 1 1 x1 times x1, so which is going to be like the terms of the curvature, beta 1 1 x1 power 2 and beta 2 2 x2 power 2. So my hypothesis test, the null one is that the beta 1 1 is equal to 0. Beta 1 1, if it's equal to 0, in fact, it's like that we won't have any curvature in our model. And or H1 is the beta 1 1 is not equal to 0. I found this equation very helpful when you want to do the hypothesis test. It's like that, I got it from the Montgomery book, like the reference book that we have. So we would say sum of the square of the pure quadratic terms that we have, it's going to be number of the factors that we would have times number, like here we would have like, let's say 4. If I just had 2 factors, so the number of the runs 2 power 2 is going to be 4, right? And then the number of the center points, so the number of the center points is like that, how many number that we want. Here it was 1, so we just considered 1 center points, but we could have replication as well, right? And then we would have the y at the y bar for these factorial runs minus the YC. So if these ones are almost equal, so this one is going to be 0, so SS of the pure quadratic sum of the square of it is going to be 0, right? So this sum of a square has a single degree of freedom as well. Just consider it if you want to add it later to your ANA whatever. Now let's say, look at the situation when the curvature is significant. These are, in my opinion, these are very interesting. So far in our class, we have learned the concept very well. I can say that from your progress. So it's good that we learn these ones, like learn the concepts behind these. Like, let's keep up the good work together. And because of that, I added these slides. So look at here, we have like intercept, main effect, interaction, and here you can see that we have curvature. Like we said that the curvature is significant. Like y1, like y bar of the C, it wasn't like equal to the y bar of the factorial runs F. So if we have this, we said that let's have 5 runs, right? So we have 5 independent runs. How many parameters do you have here? If you count them, it's 1, 2, 3, 4, 5, 6. We have 6 parameters, right? So when we have 6 parameters and 5 runs, it means that, okay, we cannot calculate the parameters from these runs. So we would need more runs, more independent runs for our system. So here we would say that, unfortunately, we cannot estimate the unknown parameters, the betas in this model, because there are 6 parameters to estimate and 2 power 2 design and 1 center point that we had, right? We have only 5 independent runs. So what was the solution? A simple and highly effective solution is to add the design with axial runs. So we have some axial runs that we are going to add it. Here, look at, this is the one that we had before, because that we had 1, 2, 3, 4, and center, the run that we would have at the center point, 5 runs. And then here is written NF as factorial runs, and NC I wrote down like in the previous slide. It's going to be the, like in 2 slides, it's going to be N for the center runs. So here we can see that, so we had, let's look at this one with 2 factors. We had these 4 runs, right, as factorial runs. We would add some axial runs. These axial runs, later you will see that we call it star runs as well. So in some books, like even in Montgomery, he uses axial as well as a star. But you can use it, like especially with the third, like 3 factors when we have, it's really very similar to star runs. So now let's look at this one. We would add the axial runs because we need more independent runs. So here I added 1, 2, 3, 4 runs. So I had like, so here is an added 4 axial runs or star runs. I already had like 4 runs from here, like main runs that I had before. Like, I mean, runs from the factorial one, full factorial one, 2 power 2, it was like 4. And I have 4, so I would have totally 8 runs, for example. Let's look at this one. When we have 3 factors. For the 3 factors, we would add 6 axial runs. Most of the time, or we call them, these runs, we call them star points, like the points that we have. Later you will see, we call them star points as well. And most of the time, these star points are equal to the double than the factors of the factors that we have. Like I have 3 factors here, so I would have 6 axial runs, which gives me 6 star points. So totally, we would have, look at here, in this cube, we had 1, 2, 3, 4, 5, 6, 7, 8, like 2 power 3. So we had 8 runs, 8 factorial runs, and then I have 6 axial runs. So I would have 14 runs, plus the number of the runs that I would have on these center points. So these axial runs, they're different than the center points. We are combining all of this. When we are adding these axial runs, we call it central composite design. So if you have heard like we use that most of the time in industrial applications. Instead of like having fully replication for our designs, we would add like some axial runs, and we're going to learn later. We have a level for these star points, which is alpha, and we're going to learn later how to calculate those. But we are going to add these axial runs to have like these points like that you can see, which we call them star points, and then we call it central composite design. So whenever you have heard central composite designs, be aware that okay, so you had your full factorial or fractional factorial, and you added some, and with the center points, let's say, to find out the pure error, and you added some axial runs. The CCD, or central composite design, is a very effective design for fitting a second order response surface model, like the ones that I showed you at the beginning. So it has the like beta 1 x1 power 2 plus beta 2 x2 power 2, and then you had the rest of the first order model, right? So now we know what is the central composite design. It's like that we're adding these ones.